law of gravitation. So we have F GMM over R squared. So you say 2 marks, right? So F proportional to the M1, M2, and then F inversely proportional to the square of the distance. Gravitational force is directly proportional to the product of two masses and inversely proportional to the square of the distance of separation. A2, use Newton's law of gravitation to show that gravitational field strength at a distance r away from a point mass m is given by gm over r squared. Okay, so this is the point mass, and then I am at a distance r away. So let's say this is my m, small m. And then we have gravitational force pulling it towards mass 1. This force F given by our GMM, GMM over R squared. The same force is the weight of the mass. Gravitational force is the weight. So normally we do also W equals to mg. So this one can go in here. mg equals to gm m over r squared. Cancel. Then we get gm over r squared. Okay, B1 show that the gravitational field strength at the surface of the moon due to the mass of the moon is 1.62. Gm over r squared, 6.67. Mass of the moon, 7.35 to 10 power of 22 divided by 1.74 10 power of 6 squared. 1.619. This is 1.62. Explain why there's a point X on the line between the centers of the Earth and the Moon where the resultant G is 0. Okay, so here's the Earth, and the line between the Earth and the Moon, you will have a 0, a point where the gravitational field strength resultant is 0, simply because if I put an object here, now let's say, let's find out roughly where is the point of 0g. If you see the Earth the mass is so large, so the stronger the g for the Earth and the weaker the Moon. So if you want to find a neutral point, the point will be more towards the Moon because this is weaker. Weaker, if you want to balance the greater one, of course, the point is going to be more towards the moon. So let's say somewhere here. Okay, this point is where the G is 0. So we have the G of the Earth, GE, and the G of the moon. Now, gravitational field strength is just another word for gravitational acceleration, right? So it's a vector and it has direction always pointing to the center. So that is how you explain it. Why you want to say why there is a 0 point? Okay, because the G is a vector and there's a point where the G of the Earth balance out the G of the moon. The field strength at point X have equal magnitude but opposite direction. Okay, idea that G is a vector quantity. Calculate the distance x of point X from the center of the moon. Right, so we're going to use the same diagram here. I want to find the x from the moon, this distance here, x. And then let's see what we are given. We have the distance between the Earth and the moon, 3.84 times 10 power of 8. So the total distance, 3.84 times 10 to the power of 8. And then let's name this RE. Okay, find X. So I'm going to use the G, start with the G. G E equals to GM. Then we write, okay, GME over RE squared equals to GMM. This is the mass of the moon over X squared. Cross off, then we get ME over RE squared, MM over X squared. Now, we're going to substitute the RE with RE can also be written as 3.84 minus this X here. Okay, so our equation becomes only one unknown. 3.84 times 10 to the power of 8 minus X. This square, this will be square. Okay, so ME 3.84 times 10 to the power minus X squared equals to MM over X squared. Okay, then bring the M equals to 3.84 X squared. Square root ME over MM 3.84 times 10 power of 8 minus X over X. Okay, so let's calculate the left-hand side. ME is 5.98, 1024. Mass of moon. over x. Final answer should be 3.83 times 10 power of 7 meter. Did I put the wrong value? Okay, sorry, this one should be 7.35. This one should be 7.35 times 10 power of 22. Okay, 9.02. Plus x, so 10.02 x. Okay. All right, let's go to the next one, question 2. Right, a sphere of mass 1.6 times 10 minus 10 kg has a charge. It's a positive charge. Sphere is in a uniform electric field that acts vertically upward, as shown in the figure. So this is showing side view. The force exerted on the sphere by electric field causes the sphere to remain at fixed vertical height. So when you see it says fixed vertical height, that means forces must be balanced. So you have the mg, and then you will have another force upward. So this is a positive charge, right? So positive charge, if you're in the field, look at the field direction. The arrow of the field is showing the movement of a test positive charge. So if this is positive charge, then it would take the same movement as this one. The force will be acting upward. This is the electric force. Okay, this will be balanced. So it's vertically in position. There is a uniform magnetic field in the region of the electric field. The sphere moves at a speed of 0.878 in the horizontal plane. The magnetic field causes the sphere to move in a circular path, as shown in the diagram here, right? This is view from above. So let's see these two diagrams. This one is the side view, right? Side view, and view from above, it is moving in a circle. If it's moving in a circle, there must be centripetal force. So here is the center. Centripetal force is acting towards the center. Now, from the question, also one thing is that take note of this. This one is what is this? Electric field lines out of the page. Okay, this is not magnetic field. This one you see the dot and then there's a circle one. These are electric field. Magnetic field is without the circle one. But they will label for you also. All right. So from top view, you look down, it is moving in a circle, but from side view, it's like moving here, okay, like this. Right. From the question, A1, determine the direction of the uniform magnetic field. Now you want to find the magnetic field. We're going to use our Fleming's left hand. Why left hand? Because you have current. The positive charge moving, current is produced. And current direction is the same as positive charge direction. Okay, so current is the flow of positive charge. So let's take one point. At any instant, at this instant, it is moving in this direction, V. So we're going to point our middle finger, left hand, middle finger to the right. And then the force, your thumb is going up. Then your index finger is pointing into the page. So magnetic field will be into the page, X. Okay, not this shown on the diagram. This is electric, this is electric field. So we are finding the direction of the magnetic field. Even if you take the point over here, it is going in this direction, the V at this instant. So your middle finger, you point up, your thumb is to the left, the centripetal force or the magnetic force is to the center. Then your index will still be pointing into the page. All right, again, your field is inward. So in this diagram, right, your magnetic field is into the page. What about in this diagram? This is side view. If top view is into the page, side view will be downward, right? It will be downward like this. This is the magnetic field. It's like you're seeing from above, it's into the page. But then in the side view, the magnetic field is going down. So A1, direction of the uniform magnetic field, we will say it is, right? You can say into the page, but you're gonna take, say for figure 2.2. I'm gonna say here vertically downwards with respect to figure 2.1. Okay, let me do vertically downwards. This is figure 2.1. Explain why the motion of the sphere in the horizontal plane is circular. Okay, because magnetic force is perpendicular, you have to mention perpendicular to velocity vector. That's the first one. Second one is that you have centripetal acceleration. Magnetic force is perpendicular to velocity vector. Second is magnetic force produced calculate the strength of the uniform electric field. Right, so electric field, let's go back to here where they are balanced, right? So electric force acting is balanced by the mg. So we're going to use that from here. F equals mg and electric force given by EQ equals to mg. E equals to mg over Q. By considering the magnetic force on the sphere, show that the flux density of the uniform magnetic field is 0.14 Tesla. So flux density is like the field strength, okay? Like the 9.81 for the gravity, and for the magnetic, they call it flux density, the B. So you're going to use this by considering the magnetic force. So we know magnetic force is centripetal force. So B, what's the magnetic force formula already? This is a point charge, right? A point charge, the formula is BQV. Okay, F equals to BQV, so equals to the centripetal force, mv squared over R. Okay, state what is meant by ideal gas. A gas that obeys, you just say a gas that obeys PV and RT. Yeah, that's it. Okay, following the answer scheme, gas that obeys PV and RT. All right, number 2, calculate the amount of mole of the gas. So just do PV equals to RT over PV over RT. 0.24, 8.31 into temperature, change to Kelvin. This one's 17 plus 230, 73. All right, you get 11.95, 12 mole. Okay. The gas undergoes 3 successive changes. Initial state represented by point A, gas is cooled at constant pressure to point B by the removal of heat energy of 48. The gas is then heated at constant volume to point C, and then again expand at constant temperature. So isothermal, same temperature as we go from C to A, back to its original pressure and volume at point A. During this expansion, the gas does 31.6 kilojoule of work. Okay, let's see. Show that the magnitude of the work done during the change AB is 19.2. Work done, so it must be, there's a change in volume. So during AB, from A to B, volume decreases. Volume decreases means that we are compressing. So we are doing the work on the gas. Okay, it's a positive work done. So we get work done is the area under the graph. So from A to B, we get the area under the graph. This is 1.2 times 10 to the power 5. Constant pressure. Change in volume is 0.24 minus 0.08. Okay, so I'm going to write it down here. 1.2 times 10 to the power 5. (19.2 kilojoule). Okay, number 2. Complete table 3.1 to show the work done on the gas, the thermal energy, and the increase in internal energy for all the stages. Okay, let's do the AB first. Now we have the formula written down first here. Change in internal equals to the thermal plus the work done. Okay, so remember the work done, if it's gas doing work, it would be a minus. Now change from AB, work done on the gas. This is the one that you calculated, right? 19.2. From A, you compress to B. I'm doing a work of 19.2 kilojoule on the gas. Thermal energy supplied to gas, you see a negative 48, that means the heat is being removed. Okay, so the heat is being removed from the gas. All right, increase in internal energy. This one we just do with the formula here. Okay. Here, minus 48 plus 19.2. This one we get minus 28.8 kilojoule. Okay, so this one is minus 28.8. Now, for BC, Work done on the gas. Now from B to C, here you go up is the same volume, 0.08. So if it's constant, there's no change in volume, there's no distance traveled, there will be zero work done. Okay, no work done. That means this will be zero. Okay, there must be expansion or compression for work to be done. It is zero. Now, if you see here is a bit tricky one, because thermal energy, we don't know, and increase in internal energy, this one also we don't know. Okay, if you look at, let's look at CA first. Maybe this one, we work out the value here, and then we go back to BC to find these two values. If you see CA, CA work done on gas is minus 31.6. What is CA? CA is from here to here. The reason we look at CA first is because it's given here. We have information. It says that it is at constant temperature. All right, constant temperature. And then during this expansion, the gas does 31.6. The gas is doing the work. So it's a minus 31.6 of work. Okay. Now we want to find the increase in internal energy. Okay, what is the increase in internal energy? If you recall back the last week, past years, we did one very similar one. For ideal gas, we are going to ignore PE. So all the internal energy is going to be the change in the kinetic energy. And temperature is the average kinetic energy. For process CA, there is no change in temperature. There's no change in the kinetic energy. There's no change in the internal energy. So this will be zero. Okay, so temperature constant. Now, again, change in internal, Q plus W. 0 equals to Q plus W, and minus Q equals to W. Work done on gas is 31.6. So minus Q equals to minus 31.6. Q is a positive 31.6. 31.6. Okay, last is the BC. Now look at the change in the internal energy of the gas. The entire process, if I start from A, goes to B, goes to C, and come back to A. You take the overall process, come back to the original position, the starting point, the overall change in the internal energy would be zero. That means this one add up with this one must be equals to zero. If this is zero, then to make this overall zero, this must be a positive 28.8. Okay, AB is minus 28, BC is plus 28 because CA is zero. So the only way you get zero resultant, this must be a positive 28.8 kilojoule. So the last one, you just do internal energy plus W. There's no work done, right? Zero work done. That means this will be zero. So the change in internal will be the same as the heat energy. Positive 28.8. Question 4. A pendulum consists of a bob attached to the end of a piece of string. The other end is attached to a fixed point. The bob oscillates with small oscillation about the equilibrium position. Right, simple harmonic motion. The length L of the pendulum measured from the fixed point to the center of the bob is 1.24. And then you're given acceleration displacement graph. Okay, so here we notice that the displacement is the same, positive and negative. That means there's no damping here. Okay, A, state how the figure shows that the motion of the pendulum is simple harmonic. Okay, simple harmonic, we say negative gradient shows that direction of acceleration is opposite to displacement. What else? Talk about direction, talk about directly proportional. Straight line shows that A is directly proportional to X. Use figure to determine the angular frequency of oscillations. Okay, A equals to minus omega square X. And then the gradient of the graph, A equals to mx. Okay, this one is the same as this one. Gradient of the graph, you can take the midpoint and over here. This is minus 0.05. And 0.40. Your coordinate should have 2 decimal places for the y and 3 decimal places for the x, because the smallest unit is 2 decimal places. And this one smallest unit is 3 decimal places. So I'm going to write here 0.050, 0.40. And here, 0.40, 0.050 equal. This is a minus, is a negative gradient, right? So they should have a minus here also. Minus omega squared. Cancel, cancel. Then you have omega equals to square root of 2.828. 2.8 radian per second. Okay, so if you, let's say if you put like 0.4 over 0.05, without the last digit, you might have taken like 1 decimal significant figures for your final answer. Okay, but this is actually 0.40 and this is 0.050. So it makes it 2 significant figures, your final answer. Okay, let's go next one, B2. The angular frequency is related to the length of pendulum by the formula. K is a constant, so find K and give a unit. We already have the omega, so you just calculate omega equals to omega square equals to K over L. K equals to L omega square. Length from the question, it's 1.24. It's 9.7. And what's the unit? If you see the unit of K is K equals to L omega square. L is meter, omega square is, okay, omega is radian per second. If omega square is radian square second square. So L omega square is m radian square s square. But radian is not actually like a real unit, right? It's just a radian. So you can just take the ms minus 2. Okay. Usually the radian, we don't have to like write radian. If it's like just radian, it's not an actual unit. So we can just do an ms minus 2, 9.7. Okay, while the pendulum is oscillating, the length of the string is increased in such a way that the total energy remains constant. Okay, suggest and explain the qualitative effect of this change on the amplitude. So it says that if the length of the string is increased during the oscillation, but then what is the restriction is that the energy total remain constant. Okay, what happens to the amplitude? What does it mean to the amplitude? Does the amplitude increase or decrease? So we will start with, here it says total energy of oscillation remain constant. Okay, let's start with this one. Energy of the oscillation is half m v max squared. That's the total. Okay, when all the potential is converted to kinetic, that's the total energy. And also we know Vmax. Vmax is amplitude into the omega. So Vmax square equals to amplitude square omega square. We put it in, we got half m amplitude square omega square. All right, so that's your energy equation. So we have this, we can relate energy and amplitude, right? We have it in one equation, but then they said this one, they want to keep constant. Oh, we got one, we need the length, we need to put the length inside this formula, right? Because it says the length increase, and we want to see what happened to the amplitude. So you need to put the L inside here, where we get the L from your omega. Here you have omega square. Okay, omega equals to square root K over L. Omega square is K over L. Right, this one goes in here. half m x naught square and k over L. So it's going to be km x naught square over 2L E. Okay. Right, then you can relate lah. This is constant, this is constant, this is constant, this is constant. So when the length increase, the fraction is going to be smaller. So you want the x to increase also to make it the same. Or you just bring the L to the left-hand side and it will be directly proportional because if it has an x square here. Okay, so our answer here is when L increase, x naught or the amplitude will increase. Okay, a few minutes and we do we look at 5, 6. Question 6, you can try question 6. That question really tests the understanding of the Lenz's law, especially the 6C. Okay, question 5. State what is meant by rectification. Okay, rectification is converting from AC to DC. Okay, conversion from AC to DC. State the type of rectification. Okay, if you see a bridge, 4 diodes bridge, it must be a full wave rectification. Sinusoidal alternating voltage, Vin, is applied across the input terminal XY. Variation with time is given by the equation, where Vin is in volt and T is in seconds. Okay, on the figure, label the output terminal PQ with appropriate symbol to indicate the polarity. Okay, let's check the. All right, this should be, if this is positive, current goes out, go in here, goes in, goes down here, and then which makes this positive. Okay, so follow the current flow. Follow the current flow, flowing from bottom up. So this is positive, this is negative. Okay, the magnitude of the output voltage varies with time as shown. Now, this graph is showing the output voltage. This equation is your input voltage. But then the input voltage and the output voltage should be the same also, magnitude-wise. Okay, magnitude-wise, direction, okay, this is like all flip on top, but magnitude-wise is the same. On the figure, label both the axes with correct scales. Use the space below for any working unit. So we're going to bring down the equation from here, 6 sine 25 pi t. Okay, V in equals to 6 sine 25 pi t. Okay, so the peak voltage, that's the V naught. The peak voltage should be 6. So you're going to put in scale here, right? This is 6. So what scale we're going to use? This should be 0, 2, 4, 6, 8. Okay, so we're going to label 4, 8. And then also we need to put in the scale for x-axis from the omega here, sine omega t. So omega equals to 25 pi. And omega is 2 pi over period. 25 pi. Okay, cancel. 2 over 25, 0.08 second. So one cycle, 0.08 second. Now be careful, one cycle is from here to here, not half of this one, because this is like the bottom one, right, being flipped on top. So one cycle is up until here, 0.08 second. Okay, so that means our scale would be 0.02, 0.04, 0.06, 0.08, 0.10. Okay, next one. The output voltage in B is smooth by adding capacitor to the circuit. The difference between maximum and minimum values of the smooth output is 10% of the peak voltage. Okay, so on figure 5.1, draw circuit symbol for capacitor showing the capacitor correctly connected to the circuit. So it must be parallel. Capacitor must be parallel to the resistor. Okay, next one. Sketch on figure 5.2, sketch the variation with T of the smooth output voltage. So we're going to draw a line from the peak, because from the peak is where it starts to discharge. The capacitor starts to discharge, but then join to, okay, what voltage? It says down here 10% of the peak voltage is the difference. So it's like this is your peak voltage, and like this. And then from here, it discharged down like this, right? If I take the peak here, from here, this is like 10% of the peak. Okay, this is like 10% of the peak. You're going to find 10% of, okay, its peak voltage is 6. We'll do 0.6 volt. So here is 0.6 volt. Then here would be 0.6 minus, sorry, this one should be 6.0. And then here is 6.0 minus 0.6. 5.4 volt. Okay, so let's sketch it in the graph. 5.4. Okay, this is 6. 5 would be in the middle. 2 divided by 10, 0.2. 0.2. Okay, it will be roughly 7, 3.5 boxes. 1, 2, 3.5. Okay, somewhere here. Okay, let me draw a line here. Oh, wait. Come on. Okay, now this is not a straight line. Huh? When you draw is like a line like this. Curve a bit, okay? Curve down like that. You cannot draw a straight line. I draw a straight line here because very difficult for me to draw it in the screen here. Okay, you cannot draw a straight line. It's like the discharge line is curve one, like a bit like S. Okay, the mark scheme very strict. Huh? Yeah, they have to exactly 3.5 boxes measured from 4, the line 4 here. So again, you draw another one here, 3.5 here. Okay. Number 3, calculate the capacitance of the capacitor. Now, capacitance of the capacitor, so we got the formula Q equals CV, but then there's no Q given here. We cannot use that one. Instead, we can use, since a graph here is given, right, we have the discharge time. Can we get the discharge time? You're going to use we have the voltage time graph. So from the discharge equation, you have V equals to V naught E minus T over RC. Is from here we can get the capacitance. Time is the time of discharge. We can find it from the graph. V peak, we have it. V also we can find from the graph, and R also, we have R? Yes, we also have R. Okay, so it's from here we find it. So you get the discharge time, starting from the peak, 0.02. Okay, the moment it drops is when it starts to discharge. So we're going to take here until over here. Okay, this is, let me draw a line down. This is 0, if you check, 0.054. One, two, three, four, five, 6, 7. Okay, 7 boxes. 7 boxes from 0.04. So this is 0.054. From the peak here, 0.02. Okay, so that's the time of discharge from here to here. I'm going to take 0.054 minus 0.02, 0.0334 second T. This is our discharge time. Okay, so voltage is after 0.034 discharge, the voltage is 5.6. Okay, so we have all the values. Just put in here. 5.4, sorry, 5.4 equals to 6.0 E minus 0.034 over RC. Answer is 2.7 times 10 minus 4 farad. Okay, now. Okay, let's finish up one more question, question 6. Okay, 6A, define magnetic flux. Magnetic flux BA and cos theta. Okay, if assuming perpendicular, just BA. So we say product of magnetic flux density and area. Okay, second marks is area is perpendicular to magnetic field. Right, a square coil of wire of side length 12 cm consists of 8 turns. So it's a solenoid. The coil is stationary in the uniform magnetic field. The plane of the coil is perpendicular to the magnetic field as shown. Okay, the flux density. Now, flux density is like the strength of the magnetic field. Okay, the flux density is given by, in the graph, you can see from 0 to 0.6. So the first 0.6 second, the flux density increase. Okay, the way you can think of this is when flux density increase, is like this is your area, right? At first you got, let's say, 4 lines, that's the flux. Flux density increase simply means you have more lines linking it. Okay, it can be like you're moving the magnet closer, so it has more lines linked to the area. Okay, this is showing the graph showing increase in the flux density. So more lines simply means the strength is higher. So from this diagram, you can imagine like the flux is into the page. So imagine you have more lines going into the page. Okay, so the graph is showing you here more lines going into the page, linking the solenoid here. Right. 1. Determine the magnetic flux linkage inside the coil at time t 0.6 seconds. Magnetic flux linkage, so N phi. Magnetic flux is phi, right? So linkage, you just add the number of turns. So N phi equals to NBA, since this is BA, equals to number of turns 8 times inside the coil at time 0.6. So time 0.6 is over here. 400. It's milli, milli, so times 10 minus 3 Tesla. 400 times 10 minus 3 times into area. What's area? .12 times is area given. Oh yeah, the length is 12 cm. Okay, so 0.12 times 0.12. 0.046 unit Weber WB. Okay. State how the figure shows that the EMF induced across the terminal is constant. So from here we get EMF equals to, the general formula is minus the change of the linkage over change of time. Okay, so it's the gradient of the graph, of the flux linkage graph. This one I can write it as minus d NBA over dt. This. Okay, and I can also write it as minus NA, then it would be dB over dt, which is our graph lah, dB over dt. Okay, dB over dt. So EMF is proportional to the gradient. Because this is constant, number of turns is 8 turns. We don't change that. Area is also constant. So this will be a constant. Okay, this will be a constant. So EMF is proportional to the gradient of that graph. How does it show EMF is constant? The gradient is constant. So line is a straight line. Okay, so calculate the magnitude E. Now find the magnitude. We can start from here. This one, I'm going to bring it down here. E. The minus sign is just showing directions, right? Since I want the magnitude, doesn't really matter the minus sign. I can just do d NBA over dt. Okay, do I have d NBA? The change of the flux linkage. I already got it from the first question 1. You see, the flux linkage that you counted here, 0.046 is when time is 6 seconds. So if you want the change of the flux linkage, then you take the 6 seconds and minus out when it is at 0. That means you would take the gradient of this graph. The gradient of this graph. Okay, but when t is 0, we know that the b is 0. Then the flux linkage will also be 0. And phi will also be 0. Okay, so that means this I can just take the answer here, 0.046. It will be minus 0 lah, but it's the same over 0.6 second. Okay, and time up. This is 0.077 volt. Okay, one thing to be careful is that this graph, the gradient is actually, because this y-axis is b, right? So the gradient is actually dB over dt. This is the gradient, right? That means this one over here, dB over dt is a gradient. But then the NA is a constant, okay? If you take the gradient times into the NA, you will get the same answer here. Okay, or you can just straight away take your answer for the change in the linkage. Okay, now, what time is it? 9 already. Okay, let's finish the C one. The procedure in B is repeated, but the time of the terminal are connected together. Okay, the terminals is connected together. Now, state and explain the effect on the coil of connecting the terminal together during the change of the flux density. Now, this one, okay, 3 marks. First is that when you connect the coil, right? When you connect the terminal, this one connected, that means you have a closed circuit already. Closed circuit, previously you didn't have a closed circuit. When you have a closed circuit, the induced EMF will cause the current to start to flow in the circuit. If you don't have a closed circuit, you only have induced EMF, but you don't have current. Okay, very important. If you don't have a closed circuit, you only have EMF induced, but there will be no current flow. But now I connect the terminal, there will be current flowing. Okay, so you have induced EMF and you also have current flowing. All right, so the first point is going to be, you're going to say here, induced EMF cause current to flow, causes current to flow. And then when current is flowing inside, you have this magnetic field. Current flowing inside the magnetic field produce force. Okay, that's the second point. Force is produced. Okay, the last mark is the tricky one. Where is the direction of the force produced? I want to find the direction of the force produced. You see the diagram here. Is the current going to flow clockwise or anti-clockwise? Like this or the other way around? Because it didn't give you what is positive. Which one is positive? This one positive or this one positive? We don't know, right? Now, this one is where you want to apply the Lenz law. Okay, what is your Lenz law again? Lenz law, it says that the induced EMF opposes the change. Okay, what does it mean? Now, you see the graph, from 0 to 0.6 second, what is the change of my flux? Is it an increase or decrease? This is a increase. The flux increase. So the way you think of it is like this. This diagram is front view, right? Let's see side view. So here is, you're looking at here. This is the coil. Sorry, this is the coil. Okay, so the flux is like this. Right, you're looking from here, so the flux is into the page. Okay, now the intensity increase means you have more field in this direction. Okay, so how does the coil oppose the change? It will produce a field that is opposite to it. Because your change is an increase. The coil want to counter you. Lenz law says what? The field, the induced EMF, is such that it opposes the change, right? So your change Okay, it's increasing the field. Then the coil want to oppose the increasing. What does it do? It will create another field that go against you to cancel out that one. Okay, so this red line is the field of the coil. And then you're going to do your right hand grip. Your thumb points, follow the direction of the field, and then you close your grip. That's how you find the current direction in the coil here. So that means it's going to be, this is your thumb, and then you close your grip. It's going to be like this, anti-clockwise like this. As you increase the flux intensity, the coil create a field that counter that increase. So we use that field that the coil created to do this, to find the direction of the current. Okay, so the current is flowing in the anti-clockwise direction. If the current is flowing in the anti-clockwise direction, then force will be acting inward, like this. Okay, you do the left hand, Fleming's left hand, you find that force is going, pressing inward, all pressing inward. That is the final mark, okay? Because if the current was in the clockwise direction, you will get an outward force. Okay, you will get an outward force. But our answer here is force acting inward for the final mark. Okay.